AP packets next. Okay, so this is a page from chapter 12 of Pre-Calc Honors. Okay, all right. So what we did is when we were finding limits by substitution, you would take x equals -2 and you would plug it into the function, and that would give you the value of the limit, right? But when we got 0/0, right, what did we do? Well, then that we called indeterminate form, meaning, okay, you got 0/0, but that doesn't mean anything. The final limit could still be undefined, it could be DNE, it could be a number, right? It could be infinity. So what we had to do is we had to do some algebra, you know, whether it was factoring to get the limit, or we had to do rationalizing to get the limit, right? You guys remember all that? So, and we did it a little bit, you know, in the beginning as well. But today, okay, we're gonna look at another way to do this. So this is L'Hopital's rule, okay? L'Hopital's rule tells us another way to solve for a limit, to find the limit of functions that give us indeterminate form of 0/0. And this is the important thing. In order to be able to use L'Hopital's rule, you have to first get a limit of 0/0 indeterminate form. Okay? So, so to sum up, if f of a and f of b are both 0 at x equals a, then you can't find the limit by substituting x equals a. Okay? L'Hopital's rule gives us a way to use derivatives to evaluate limits that would otherwise have been given indeterminate form. So here is L'Hopital's rule. If you want to find the limit as x approaches a of f of x over g of x, and you get 0/0, what you have, so look, this is the premise. If these are both 0, then all you need to do is take the derivative of the numerator and the derivative of the denominator. Okay? So let's go ahead and take a look at an example. Let's do this example. Suppose you need to find the limit as x approaches 2, x squared minus 4 over x minus 2. Okay, you plug in 2, you get 0/0. Okay? 0/0. So what would we have to do? Okay, this is the limit as x approaches 2, x minus 2, x plus 2 over x minus 2. This goes away. This is the limit as x approaches 2 of what? X plus 2. So now this is equal to 4, right? That's what we had to do before. But if you wanted to use L'Hopital's rule, and that's the abbreviation, L'Hopital's rule, okay, we say we need to find the limit as x approaches 2, x squared minus 4 over x minus 2. Okay, what's the derivative of the numerator? Just the numerator, just x squared minus 4. 2x. What's the derivative of the denominator? 1. Plug in the 2, 4/1, you get 4. Okay? That's L'Hopital's rule. That's what it lets you do. Do you see that? So you don't have to do any of this stuff. You could just find the limit by taking the derivative of the numerator, derivative of the denominator. So let's do this. Find each limit by applying L'Hopital's rule. Okay, so first you need to check if you are going to get 0/0. When we plug in 0 here, we do get sine of 0/0, which is 0/0. So you have to say that you're using L'Hopital's rule. Okay? So this is the limit as x approaches 0, cosine x over 1. Now put in a 0. What do you get? 1/1, which is just 1. Isn't that cool? Yeah? Okay, so the next one is a similar example. Put in 2, you get 0 over 0, so we must use L'Hopital's rule. When you take, so it's the limit as x approaches 2, 1 over 2x, plug in the 2, 1 over 4. Yeah?
So the limits are solvable if you do the other way, but
this is just a shortcut. Yep. Okay? All right, so take a look at this one. Tangent of x over sine of x, right? This one, we would have had to do, like sine over cosine over sine and then cancel things out, whatever. Or, we would get 0 over 0. So by L'Hopital's rule, limit as x approaches 0, secant squared x over cosine x. Okay? Plug in 0. Secant at 0 is 1 over 1. You just get 1. Okay? So take a look at that next one. That next one, if I wanted to put in a 1, I would get 0 over 0, right? So the way in which we had to do it was this, by rationalizing. You see that? Okay? But now, with this, we no longer have to do that. You just say, hey, I'm using L'Hopital's rule. So this is the limit as x approaches 1 of, what's the derivative of x minus 1? 1. What's the derivative of root x? Okay, so root x, it's time. Let's just memorize. The derivative of root x is 1 over 2 root x. Okay? Minus 1, that gives you 0. So this is, if you simplify just 2 root x, do you see how much simpler that is? Right? And then now just plug in the 1 and you get a 2. Okay? Now, of course, there's always an exception. There's always a glitch. Sometimes you can do L'Hopital's rule, but you still get 0 over 0 when you plug in x equals a after doing L'Hopital's rule. So guess what we have for that case? We have the stronger form of L'Hopital's rule. Okay? And what that says is you basically just do it again. Okay? All right. So take a look here. Take a look at what happens here. When you put in 0, 1 minus 1, 0 over 0. So we're going to apply L'Hopital's rule. So we're going to get here sine of x over 2x. Okay, so you put in 0 now, and you still get 0 over 0. But don't worry, you just do it again. Just keep doing it again. Cosine of x over 2. Now put in a 0, 1/2. Okay? Otherwise, what would you have to do? You would have to multiply top and bottom by 1 plus cosine x, square it. You would have gotten 1 minus cosine squared x. That's a trig identity, right? And then, you would have to do all sorts of different things. But this one, just do it. Okay? All right.
What is 1 minus cosine x again?
1 minus cosine squared x. 1 minus cosine x is nothing.
1 minus cosine.
1 minus cosine squared x is sine squared x. Yep. Are you running a note to yourself? No, but was it the sine squared x?
Huh?
I thought you were writing down what 1 minus sine squared x is.
Oh.
No. Okay, hang on. It just looked that way. Okay, so here we go. We put in the 2. Just trust me on this. You get 0 over 0. So L'Hopital's rule says this is the limit as x approaches 2. 2x minus 4 over 3x squared minus 12. Okay, put in a 2. right? And I get 4 minus 4 is 0, not cool, over 12 minus 12 is 0 again. So let's just do L'Hopital's rule again. So what do I get in the numerator? 2 over 6x. Now when I put in a 2, I just get 1/6. Okay? Oh, I love the ones with the e's. So look, e to the 0 in the denominator is 1, minus 0 minus 1, so that's 0. And then 0 on top as well. Okay? So using L'Hopital's rule, every time. Every time. Yep, every time.
And the limit?
Yep, every time. You have to put the LH and the limit at every single step. This little LH.
Okay, from here it looks like LM, so I was so confused the whole time. I was trying to figure out what it's.
In the beginning, I thought it was LM, and then I noticed it was LH, and LH makes more sense.
It's LH for L'Hopital.
Yeah.
And this is how it's like universally known by LH. Huh? Yes, he was a guy. He was, huh? Yeah. His name is L'Hopital. What? Is it Anton? No, it's not Anton. It'll come to me. The first name will come to me. He's French. He was French.
They're good at Calc.
I mean, are they though?
Who was the other one? Newton? No, who's the other one?
E to the x minus 1. Okay, when you plug in 0, you still get 0 over 0. So let's do it again. L'Hopital's rule, LH. Limit as x approaches 0, 2 over e to the x. That's just 2. You gotta love e to the x. Okay? Now, we can also use L'Hopital's rule for one-sided limits, right? So take a look at this one. It's the limit as x approaches 0 from the negative side, but that's okay. When we still plug in 0, you still get, 0 over 0. So remember how we used to do this one, right? It was we had a like sine of x over x. Remember the limit as x approaches 0, sine of x over x? That was a property way back in chapter 2. We're going to revisit that as we're doing our AP problems. But this one, since you get L'Hopital's rule, since you get 0 over 0, you can say by L'Hopital's rule, this is the limit of 4 cosine 4x to sine 2x. Look at how those derivatives just like, made a little comeback. Just kind of like slid back through the door. 2 cosine 2x. And so now, when you plug in 0, right, cosine of 0 is 1, so that'll just give you 4 over 2, which is 2. Okay? All right, next. Tangent of 0, 0, x squared is 0, so this is going to be another L'Hopital's rule. Okay, so secant squared x on top, 2x on the bottom. Do we need the stronger form? What's secant at 0? Secant is like cosine, so it's 1. So we get 1 over 0, right? Which is dne slash. Is it, okay, so what is it, positive or negative infinity?
Negative.
Negative infinity because it's from the left side of 0.
So is that the only time it would matter from right to left? If it's positive or negative? That makes sense? Because I don't understand why the first one, why it matters which side is left.
Why for the first one it doesn't matter?
Well, now you can check
Yeah.
using the other one.
So here, when you plug in a number for cosine, whether it's cosine of like a positive number or a negative number, it wouldn't matter, right? Because cosine doesn't differentiate between positive or negative. It's an even function. So you still get like positive 4 over 2. But here, when you put in 0 into the secant, you would get 1, because it's squared anyway. But here, it's 2 times x. So what number are you plugging in? You're not technically plugging in 0. It's like negative 0.000001. So you would get a negative answer. It would go down to negative infinity. Okay, there is an asymptote there at x equals 0, remember? And to the left of the asymptote, the graph is going down to negative infinity. Okay, now, another type of indeterminate form is if we get infinity over infinity. All right? And those are the only 2 cases that we're going to look at. Because there is also a situation with 0 times infinity. There is, so those are different cases. The only cases where you're going to be allowed to use this is if you get 0 over 0, infinity over infinity. So L'Hopital's rule can also be applied there. So take a look at this one. You have the limit as x approaches infinity of ln of x, which is infinity, and x squared, which is infinity. So this does give you infinity over infinity, which means you are allowed now to use L'Hopital's rule. So this is going to be the limit as x approaches infinity. What's the derivative of ln of x? Thank you, 1 over x. And of x squared is 2x. So this is the limit as x approaches infinity of 1 over 2x squared. And as x approaches infinity, this whole thing will approach what? 0. Okay? All right. 1 over a very large number is 0, as the denominator gets, right? Okay, so here, remember the graph of secant, right? Secant graphs look like this. Remember? So at pi over 2, the secant jumps up to infinity. So that's infinity. And then tangent at pi over 2 is also infinity. So by L'Hopital's rule, this is going to be the limit as x approaches to pi over 2 of, what's the derivative of 1 plus secant x? All right, this is good review. Over secant squared x. And one of these cancel with one of these. So this is the limit as x approaches pi over 2. Tangent over secant. Okay? And here we can also actually do a little bit of trigonometry. Okay? So what's tangent these days? Sine x over cosine x over 1 over cosine x. Right? The cosines cancel. So you just have the limit as x approaches pi over 2 of sine x. And how much is that? 1.
Oh my god.
It's pi over 2. Okay. Ooh, look at the next one. I love the ones with the e to the x and the L'Hopital's rule. I really do. Okay. So, e to the infinity is infinity. Root x, if it's infinity, is also infinity. But see, like, you can't cancel those out, right? Because this infinity and this infinity are not the same infinity, right? Like, e to the infinity, e to the, a very large number, like, goes up much, much, much higher, right? So, for example, like, if you take e to the million and the square root of a million, yeah, they're both large numbers, but they're not even, like, close to being the same thing, right? So you can't cancel them out and say, oh, they're both infinity, let me cancel it out. No, like, you can't do that, yeah? So, so that's indeterminate. Okay, so if we use L'Hopital's rule, okay, this is the limit as x approaches infinity, e to the x over, what did we say the derivative of root x was? 1 over 2 root x. Limit x approaches infinity, e to the x times 2 root x. Now, e to the x goes to infinity. 2 root x also goes to infinity and infinity, so together their product is also infinitely large. Now we're allowed to say this is infinity slash DNE.
So you want to do stronger?
No, because that doesn't apply to infinity times infinity. Okay? Do you see how, like, there are still rules, right? Yeah.
We have to put, like, positive infinity.
If it's positive infinity, you don't have to put the plus sign. Okay. All right. Ooh, look at the next one. So clearly, again, infinity over infinity. So by L'Hopital's rule, we get 6 over, all right, quiz time. What's the derivative of 2 to the x? What's the derivative of e to the x?
E to the
E to the x. Okay, what's the difference between e to the x and 2 to the x? Not much, same form. So it's still 2 to the x, but there is... Yes.
Yeah.
Yep. 2 to the x times ln of 2. And this is how you're going to remember. Well, first, you're not going to forget anymore. But if you do, this is how you're going to remember. I know e to the x. 2 to the x isn't much different, so it must be the same form, 2 to the x. Then you're like, wait a minute. Even for e to the x, right, that was e to the x times ln of e, technically. But since ln of e is 1, we don't ever have to write it. Yes, see? Math is consistent. So, now, okay, so we have 6 over 2 to the, a number that's infinitely large times ln of 2. What do we get?
6 over 2.
6, right? 6 over an infinitely large number, which would be 0. Yay. And this was L'Hopital's rule. Good old L'Hopital. Got